Okay, let's do an example with uniform circular motion. So let's imagine we have a space station. And so the space station is in the form of a giant ring and has a diameter of, let's say, 50 meters. And we have have astronauts in here. Now the problem is in space that if you don't have gravity, your bones and muscles start deteriorating. The way you're designed is as a human being to have gravity pushing down, the ground pushing up, and this compression in your bones actually strengthens them. If you don't have that tension or the compression in the bones, then what happens is that you leach calcium out. So many astronauts, when they come back from space, have the equivalent of severe osteoporosis because of this. And so there's all kind of strategies that they've thought about for long duration space missions. Well, one possibility is if the space station rotates. Now, if it rotates, that means that for an astronaut going around with the space station, there's going to be centripetal acceleration. That centripetal acceleration we learn in chapter 5 that F equals ma. So if there's an acceleration, there's a force. And so that means that that force pushing down, pushing up here rather, is going to be similar to the ground pushing up to offset gravity. And so that's going to compress the bones. And so that's the key. And so what we want to do is calculate for this particular case. We want to calculate how fast the station has to rotate so that it simulates. Now, it turns out your body doesn't need a full 1g, but if the centripetal acceleration were equal to 0.65 g, then that would be sufficient to keep your bones strong. Okay. So what we want to do is figure out how many times per second. So that's the period. Period is the length of time it takes to go around. And so how many times per second will this thing have to rotate? Okay. So centripetal acceleration turns out to be v squared over r. Well, our space station right here is 50 meters in diameter, so r is 25 meters. Okay, so that gives us r. Now, what about v? Well, the distance around divided by time is going to be v. So 2 pi r divided by the time it takes to make one rotation is v. Well, the time it takes to make one rotation is period. So we often use the capital T to indicate not just time, but this one special time, the time for complete rotation. And so that means that v squared is going to be 4 pi squared r squared over t squared. So if we plug that into centripetal acceleration, we have 4 pi squared r squared over r t squared. So then the r's cancel. And so we look at this, we say, well, this is pretty straightforward. Okay, so t is going to equal 4 pi squared r over, or rather, t squared equals 4 pi squared r over ac. Okay, so that means that t is going to equal 2 pi square root r over ac. So t equals 2 pi square root r over ac. Well, we said that ac only has to be equal to 0.65 g. And we realize we've got everything that we know here. 2 pi square root of 25 meters divided by 0.65 times 9.81 meter per second squared. So the T comes out to be So this comes out to be 12.4 seconds. So that means that this giant ring in space has to rotate once every 12.4 seconds. Well, now the question is, well, how fast is the edge of it actually moving? So V, okay, equals, R times theta. Okay, or sorry, not R theta, but R omega. Okay, we know that, but I want to know it's also equal to 2, so we also know it's basically equal to the distance around over time. So in this case, that's 2 pi times 25 meters divided by 12.4 seconds. So that would be 12.7 meters per second is how fast the edge is actually moving. Okay. Which means that if you have an astronaut in here and they're running in this direction, they're going faster. So what does that mean? Well, centripetal force is V squared over R. So as they're running faster, the centripetal acceleration is going to be more, so they're going to feel heavier. If they run in the other direction, their total velocity is going to be less, and so they're going to feel as if they weigh less. And so if you run in the direction of the rotation, you feel heavier. Run the other direction, you feel lighter.